Okay, thank you for your patience. Shiv specifically, thank you. Such abuse in the front row. Okay, oh, block 7. So ready or not, I'd like to see what you got. Do you have a question, Augie?
That's fine.
Yeah, I'm about to do this. I appreciate the initiative, but okay, so I need all the talking to stop. Um, yeah, I'll give you a chance to talk about this a little bit later. I forgot to mention, are we okay with this date?
Yeah.
How are you supposed to do this?
There's the 8.
Just like it didn't say it. Yeah, where does 6 come from? You can, yeah, the 3, 4, 5 triangle. Do you see that? The 6, 8, 10. Yeah. Where 10 is the, how do you know 10 is the hypotenuse? Because the thing subtract c squared minus, and then one of the sides. So we have 10 squared minus 8 squared. 10 is the hypotenuse, 8 is the leg, the other leg is 6. Just look at it quickly. Or you could think about the inside as a difference of squares and factor it into 2 times. For those of you at home, we're doing this right now. You can factor that into 10 minus 8 and then 10 plus 8. This is not a great way to do it. This is just for fun though. 2 times 18, which I think is the same thing as 2 times 9, isn't it? And then we know the square root of 4 is 2, square root of 9 is 3. Yay. Okay. Anyway, that's beside the point. I do want you to see the 6, 8, 10 there. So, but let's see what this person has to say about this problem. Nathan, what'd you do for this?
Alright, so basically, the first thing that sticks out to me is like the 3 and the 4, so I think of like a 3 and 5 like triangle.
Okay.
So I mean, I just drew a triangle. I don't. You don't have to. I just do like, because it's cosine, we know that the adjacent over the hypotenuse is like 3 or 4, so which means like one of the sides is 3 and the hypotenuse is 4.
Okay. And before we go on, I want this triangle to be very specifically placed. I want it to be very specifically placed. Considering this is a cosine inverse, could you all show me exactly where this triangle should be? Just show me where it should be. So I'm seeing here in the second quadrant. Good. Okay. So I imagine that I don't know if you put in the second quadrant, it's okay if you didn't, but that's fine if you just drew a triangle. So I'm gonna put this triangle here, and you said that the adjacent is,
The adjacent is 3.
and we'll put this -3 here, and then of course the hypotenuse is 4. Should I just fill in a 5 right there? Would that be a good idea?
That's only the 4 with the other way.
Yeah, so what do I do? Is this possible?
And, you know,
Okay, what do you get when you do that?
um,
Are we good with that? Nice.
and then
Any questions about that? Yes, we do. All right, remember, anytime you see an inverse trig, that's referring to the angle at which that occurs. So whenever I see this, I think, oh, that's just an angle. Here's our angle for which cosine is equal to -3/4. And the rest kind of just falls into place. Is this problem very different? It's kind of the same, but we no longer have a number, we have a letter. How is this possible? Yes, Nia, what should we do? Okay.
Why?
Okay.
What why that, like, what data has to be such that why the.
Okay. Now this is a little bit confusing because you're talking about x on the unit circle and you're talking about x in the context of this. And I don't know, is it the same x?
Or I guess it could lose another value, but the value that we want x to be on the right should be the same value as the value.
So what do you do?
I thought the coordinate of. 3 and 5 is 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 I just need that like
Yeah, I'm gonna save you from yourself right here. You may be right, but you're going to a place where it's a little dark and scary. I'm not saying you're wrong. Thank you. On the other eye. Close. So do we do it the same way as the last one? Yeah. Where should we put our triangle? But either quadrants, 1 or 4. Let's keep it simple and keep it in quadrant 1. Okay, so we have this triangle. Yep. Okay. I made that. Okay. Does that make sense to make the like force a ratio there? And yeah, I'm sure you got to something like this. But how would you get the hypotenuse? Would Pythagorean theorem get you the hypotenuse? No? You doubt the Pythagorean theorem? Shame. Shame. Yes, Aki.
Oh, wait,
Yeah, tell me, what should we do?
So you could just set up like normal, so x squared plus 1 squared equals,
Let's call it h squared again.
sure, yeah, h squared. But then you would know that h squared is equal to x squared plus 1, which
Mhm.
means that, or sorry, 1 squared, but 1 squared was just 1, so which means that you would know the hypotenuse is just x squared, or sorry, square root of x squared plus.
Are we good with that? H is equal to square root of.
And then you just solve it.
Can we simplify square root of x squared plus 1?
Like,
Could we? No, no. Only factors. So you're right exactly as you first started. But is this helpful?
yeah.
Yeah, but now we're looking for the cosine of the angle, which is 1 over this guy. Yeah. So I know there was a little bit of their homework that kind of went into something like this, and I didn't talk about it, so I just wanted to make sure to touch on that before we continue with today's lesson. Today's lesson will not be from the packet. Haley, did you have a question?
Just to make it more difficult, they can change 1 to the x value and still get the same notation.
So like if you did something like made it 2x over 2, because we still need it to be x. We could do that. That'd be fine. So then this would be like 2x right here. This would be a 2 right here. But then we'd have like 4x squared plus 1, I believe. No, it would be plus 4, wouldn't it? If I had that. And then I factor out the 4. It works out. So we keep the simplest. And I trust that will always be the same. But good question. Yeah, it doesn't have to be x and 1. It could be anything else as long as the ratio is x to 1. Yeah, Nia? It has nothing to do with the unit circle. So that's the dangerous thing, and that's what you were crossing wires with before. This is all I'm thinking here is, remember, this is an angle whose cosine is -3/4. This one is the angle whose tangent, well, I already wrote it here, whose tangent is x, and I need to force a ratio. Yes, it's just a number. In this case, it's a variable, though.
Okay.
Yeah. You sure? I have to tell you a little anecdote. Just have to tell you. A student came in and talked to a teacher who's sitting next to me several years ago. They were teaching honors pre-calculus, and they were going through this problem. They said, okay, we're talking about an angle. Where is this angle? And it was established that it was in the first quadrant. So the teacher asked the student, okay, go ahead and draw a triangle in the first quadrant. So honors pre-calculus, this is what they do. I gasped. I tried not to. I tried not to. But yeah. But what's wrong with that triangle in the first quadrant? It's a triangle first quadrant.
Not ready.
Or the angles we deal with are in what position? Standard position comes from here and goes to, like, it has to include that X. So at this point, it's just a joke. Yeah, I think they jumped. Yes, I think so. Yeah. Yeah. Anyway, yeah, as I promised, today's notes are not in the packet. So you ready? Maybe I'll reference the packet a little bit just for fun. Either would that be okay with you? Okay, it's a good packet generally. Really?
Yeah.
Contrast.
I was gonna, I like the no pack.
Oh, the no packet. Oh, I thought it said notes packet. Oh, okay. Yeah.
Yeah, PR.
Identities. Do you know what an identity is in mathematics? Maybe not. I don't know if you've spoken about identities. It's an equation for which the solution is all real numbers. For instance, x equals x is an identity. But we're going to be talking about trigonometric identities today. And the first one I'm going to talk about is, and you already know 6 of them. You know, cosecant of theta. You know this one, don't you? Yeah, this is equal to 1 over sine theta. Yeah. Yay. And next to this, we have sine theta is equal to 1 over cosecant theta because they are reciprocals of one another. I think you know the next 4 that I'm about to write. You want to race? Okay. Ready, set, go. Uh-oh, I'm nervous. What? And you have such nice writing. Oh, I'm so slow. Okay, there we go. Done. These identities are called, to no one's surprise, the reciprocal identities. And we know 2 more. Do you already know which other 2 I'm talking about? Yeah, we know that tangent of theta is equal to sine theta over cosine theta, and we know that cotangent of theta is equal to cosine theta over sine theta. Okay, 8. We have 8 identities. And we're going to do a whole lot more today. Oh, these are not called reciprocal identities, although they are reciprocals of one another. These are called, starts with a Q. The quote. Cute. Just anywhere that starts with a Q. Cute. I think cute starts with a K, doesn't it? This is Shiv, you got it, of course. Quotient here. Quotient identity. It's not quadrant. It's quotient identities. Okay, this next one. Yes, the queer identities. Good. This is 1 and this is theta. Do we know that bottom side? Do we have any idea? Oh, no. I can check with your neighbor. What are the lengths of the other sides?
That's just.
Don't make it a specific like pi over 3 or pi over 6. This is theta.
Oh, 35.
Oh, like
Why not?
It would be.
Do we know it?
Oh, yeah.
Oh my goodness. Okay, I'll call this an X. What tool do we have to figure out X?
Oh. Oh, it's these ones.
If you're giving it a number, I'm quite disappointed. It's not a number. It's going to be an expression. What relates one to theta and X? Cosine, doesn't it? So we're going to do a little bit of work here. Cosine of theta is equal to X over 1. And oh my gosh, X is equal to cosine of theta. Have we ever seen that before? That's from the unit circle. Do you know the other side? Are you sure? Really?
Oh.
It's not root 3 over 2?
No.
It's only root 3 in a very specific instance, right? But it's always sine of theta. Yeah. Nothing new here, but we're about to do something that may be new for you, but or maybe you did this last year. The next set of identities is called the Pythagorean identities. Yes. So do you know what the first one is already? Sine squared theta plus cosine squared theta equals 1. Related to this, we could say that sine squared theta is equal to. Do you see very clearly that sine squared theta equals 1 minus cosine squared theta? And also cosine squared theta equals. That's all the same identity, just twisted around. So, okay, so that's one Pythagorean identity. There are two more, though, that you need to know. Yeah, two more. Can you believe it? Yeah, they have to do with the cos and all the rest. What I'm gonna do here is I'm gonna divide everything by. I'm gonna start with cosine squared theta just arbitrarily. So what I'm doing here is I am deriving another Pythagorean identity. Do you see what that first expression becomes?
Yeah.
Does that make sense that that's tangent squared of theta? So this is a second of the Pythagorean identities. Tangent squared theta plus 1 equals. And what is 1 over cosine squared theta? That's secant squared theta, isn't it? So there's a second Pythagorean identity. Oh, you had to memorize all of them in ninth grade? Wow, nice. Would you please find the third one? Okay. So you're just writing the third Pythagorean identity. Did you get it?
Now we use fine.
Instead of dotting everything by, just make sure the people around you got it. I'm gonna call on one lucky person to tell us what they got. Okay, what you get? One plus. Squared. Are we good? For the first many years of using this, I only memorized one. I just memorized this one. And any other time I had to use the others, I would just do something like this and then just divide everything by whatever I need to divide by to get the other ones. Just I don't have a lot of storage space up here. So I had to be mindful of what's going on. Yes, Leah? Oh, these are all tools we're going to be using to solve equations and to simplify expressions and things. So I'm just giving you stuff you'll need. Simran? The quotient identities. Yes. And these are called the Pythagorean identities. Should I write that down? I'm not going to. Taking a stand. Okay, I'm gonna reference the packet just for a little bit. Just for a tiny bit, okay? Just a little bit. Not too much. Okay. We're gonna do example 1. It says to rewrite f of x as an expression involving tangent of x and no other trigonometric functions. Oh, thank you. This is page 20. Step 1, I'm going to write this as sine of x times secant squared of x times. Would it make sense now to say times 1 over cosecant x? I think you're right, but I mean, just right now, I hope that this makes sense. This is the same thing as this. Well, I'll give you a chance to now go ahead and use the identities that we have to simplify. So I'm just kind of parsing it out as such. And you're using the identities we talked about today to simplify these.
I got it. I got it.
Yeah, it should be satisfying. There should be some satisfaction here.
I am.
You got it. Oh, good.
It makes sense.
But isn't it nice? Make sure Nathan's got it too. Make sure. I'll give. I can put your hand. Man did well.
Here, wait, let me.
I guess so.
I'll block it. What I'm doing right now is like.
Okay, we're ready? 10 seconds.
Oh, yeah.
Okay, Oliver, can you help us out with this? What'd you do?
Yeah, I got it.
Thank you.
Okay, so. 1 over cosecant x is sine of x, and so you get sine of x times secant squared of x times sine of x, which is just sine squared x.
Okay,
times secant squared x.
nice.
So secant squared x is equal to 1 over.
I'm gonna do it all together if you don't mind.
Yeah.
Okay.
And so then you just multiply it, so you put sine squared x over cosine squared x, which is 2 sine squared x times 1 over cosine squared x. So then you have sine squared x over cosine squared x, and then you take the square root of it, of the top and the bottom of the unit.
Wait, can we just take the square root of it though?
Or actually, better way to, you should get tangent square of that.
And then is there anything else after that?
No.
No, we're just done there. Are we good? Perfect. That's exactly what I'm looking for. Any questions? Perhaps the question is, can we try another? Okay, this one is pretty triggy. Thank you. Let's see if we could do this. Oh, it's not tricky.
No.
No.
This is actually relatively.
Oh,
Pretty.
but it's too simple.
It was a little bit.
Oh, is it? Okay, so cosecant, that's 1 over sine theta. Tangent is what? Sine theta over cosine. Oh yeah, this one isn't very tricky. We're just left with, okay, secant theta. I did thetas instead of x's. Yeah, it would be x. Okay, let's see. Let's do a tricky one. Ah, this one, example 3. Let's try that one. That's so simple.
I mean, I'm. Over cosine. It's one that is cosine for us.
Judy, you got it? I'll give about 15 seconds. I'll call one lucky individual to help us out. Okay, so finish or not. This problem is specifically is a little bit forced. Normally it's about simplifying. Here it's like directing you to like express it in terms of only cosine. So Haley, were you able to get anything here?
I don't think I did it right.
Oh.
Okay, well, let's see what you got. Well, I'll tell you if you're going wrong.
And I use
Okay. One over sine x is like this, you mean?
Yeah, well, what if you? Yeah.
Okay.
Then, yeah, sine x squared.
Do you mind if I write it as sine squared x?
I'm sort of.
Okay. Are we okay up to here so far? This is great. This is perfect. Yes, absolutely right. The question is what now what, right? Now what? Shiv, what do you think?
So Mia had the idea of using the function sine squared x plus cosine squared x equals to 1.
Is this true that sine squared x plus cosine squared x is equal to 1? Okay.
And then it's 1 minus cosine squared x. Sine squared x will be
So you can replace that sine squared x with 1 minus cosine squared x over cosine x. That was a Nia idea. I like the brand Nia idea. Well, we're done. We've expressed it as powers of cosine. That's it. Nothing else we could, and we could maybe factor the top. The factor the top. I don't know. We're done. We wouldn't. We simplify this to get to here, and then once we thought this would be sine squared, or if you just replace that with a expression involving cosine.
But what I'm asking is why, did you say sine squared but cosine squared x equal to 1?
This is our fundamental which identity system. But I think this is I know that. So we're building
Religious base.
what's that?
That's just true.
Yeah, and that we talked about that in right here. in the warm up, right? We have that here. Right? So that's something we could always pull from.
Oh, I get it, it's just y squared. But I don't like.
Yeah, so it comes from this, yes. Okay, we're going back to away from the packet. So I'm going to continue here. This is too easy. Okay. Let's simplify this. No Pythagorean identities here.
Wait, are we on?
Don't use Pythagorean identity. It's simplifying. This is not in the packet. This is just in notes, free-form notes. I don't know.
Wait, no. Wait, no.
Can I give you a direction?
Yeah.
Let's keep tangent, and instead of cotangent, let's write this as 1 plus tangent theta over 1 plus, instead of cotangent, I'll use reciprocal. Okay, go ahead and simplify. Are you clearing the denominators? This.
Oh my god. Oh.
Get clearing of the denominators. That's the easiest way to do it. There are other ways, but. Do you need more time? Okay. I'm just gonna talk you through it. To clear the denominator, what do? Multiply top and bottom by tangent theta. Are we okay with that? Okay. On the top, I'm gonna leave it factored. I'm gonna leave it tangent of theta times 1 plus tan theta. Because I have no problem with denominators there. On the bottom, what happens when I distribute that tangent theta? I get tangent theta plus 1. Does anything cancel here?
Oh my gosh.
Yeah, so
Oh my.
it is just tan theta. Tan theta. Okay. Let's try one more. One more for now. I'm gonna give you a massive identity here. Yes? Oh, sure. Of course.
How are we supposed to know? We just have a graphic check. How are we supposed to know when we're losing without?
Right. Right. I'll give you some tips. Okay, so here's an identity. You don't have to memorize this identity. But the instructions for this one say to either prove this identity or establish it, which means you're going to do this one we just did. You're going to choose one side and simplify it until it looks like the other side. So in this case, we're going to choose. What do you want to simplify that? Use the left side. Let's see if we can simplify that. Yes, Augie, you have a question?
I just have a really quick question on the top one.
Uh-huh.
So is that, and the way you write it, is it, you put tangent theta and then like
Times. It's a multiplication problem.
times 1 plus tangent theta, and then is that the line? Sorry.
No, that's the problem. It's the fraction bar.
Oh, okay.
I multiply top and bottom.
Oh, you have flight, so I can get it.
But you have to, for a fraction, you have to multiply top and bottom by the same
Oh,
thing.
okay. Sorry, no, I was just trying to
That's a
figure
good
out-
question. No, these things take time to figure out. Thank you for asking.
Okay.
Yes, we are allowed to use Pythagorean identity. The question is, how would you do it?
Right.
I'm gonna use a little bit of a trick here. So I'm going to multiply top and bottom of this fraction only. I'm not going to get common denominators, although that might work. Yeah, I'll just multiply them by 1. I can multiply any number by 1. Yeah. That's a great question. What would I multiply by?
Cosine theta.
I multiply by the conjugate of this.
So
One minus.
cosine theta.
Yeah, 1 minus cosine theta, 1 minus cosine theta. I think this is how to do it. It's been a while since I've done this one. I notice I'm just multiplying this by 1, so it's not, I don't have to do that. And the way this works now is I'm just going to work on the left side, simplify down until I get something. Let's see what we have here. So top, I'm going to leave factored. 1 minus cosine theta times sine theta. The bottom becomes 1 minus cosine squared theta. And the second one stays the same. I'll give you a moment to figure out what to do. Just whatever you do, don't distribute up there. At the top, don't distribute, please. What can we do here? Make the top back, please. Did you get it? You got it? Let me see this.
You know what? I didn't feel we did that. There? Oh, yeah.
Yes.
What are we trying to do? Oh, basically that.
Does this look familiar with 1 minus cosine squared?
Yeah.
Have you seen that before?
Yeah.
Good. Keep on going.
Wow.
It is. I agree. Are you getting it? What happens here? I don't need to because the first fraction cancel one of the squares. Got it. So I'm left with 1 minus cosine theta over sine theta plus 1 plus cosine theta over sine theta. And that apparently equals to cosecant theta. And now we have common denominator left, don't we? And when we add the numerators, we get is it the same thing? Yeah, so this is the same thing as 2 times cosecant theta equals 2 times cosecant theta. So that's called proving or establishing an identity. Any questions? I do have to tell you one fundamental rule. Anytime you're proving an identity, you can never add, multiply. Well, you can't do anything to both sides of the equation. You can't add the same thing to both sides. You can't multiply the same thing to both sides because that's assuming it's equal. You're trying to prove that it's equal. So that's why, notice I didn't touch the right. We're going on the left side until it matched the
They not solve.
Yeah, so when we're not solving anything, we're proving or establishing identities. So that's what this was. I gave you this identity. Identity is just a statement that is true for all real numbers. Or there could be some exceptions, like if we have some asymptotes, of course. And the way to prove it is to just work with one side. Ready for a little geometry review? Ready or not? Here it comes. Do I have it here? Okay, I do. We're starting with the triangle side. Please find the lengths of each unknown side. Yeah, so you're gonna need a calculator for these. Unless you just know. You can share with your neighbor. Calculator's fine.
Your mind.
There's 3 different problems. Just set up for calculator ready. I mean, don't just sit there and do nothing.
So then you did multiply.
Oh, yeah. I don't. That's over 10. So 10 times 7. We're talking about 7. Other side, 7. Oh my God,
Well, that's fine. That's like. So like, you know, it's cosine, so you know, it's cosine to the.
That's a 5. Oh.
How do we? I don't want to be.
10 times about 3. Or that was correct.
Yeah.
That makes sense.
Or that's actually. Because this is.
Which would be radians, but.
No, wait, that's 9 of 7. I'm a little out there.
Yeah. Okay, sine of 7, we got it, that makes sense.
So,
Okay. We got that. So sine of 12.
wait, yeah, I think so. But it's over there.
What's 7 degree?
8, 9, 9.7. Yes.
Okay, A is 9.1 degrees. Your math 10 times 7 point. I think it's drawn to the side. It's like close. Wait. Okay. Sine of 0.2.
So A is I'm theta could be just the x of y of
Wait, we should be in degrees now? Or something like that.
Yeah.
Degrees for it.
Nothing for degrees.
Right. No. Wait, Wait, also tell me, yeah.
Okay, folks, your calculator, it seems like you got to that radian degree issue. You know how to tell which mode your calculator is in?
Second mode.
So it's right here. So, and it's important if you're using degrees, make sure it's in degree mode. Don't convert to degrees by hand or anything like that. Make sure your calculator is in that mode.
Either degrees. Nine. Wait, okay, wait, So. Oh, wait, no. Yeah, nine.
Wait.
Are we ready?
No.
Nine.
If there's only one calculator, please make sure you're sharing and making sure that your neighbor could switch back and forth. Great.
I'm supposed to be at.
Right there.
Okay.
Yeah. All right. Right, this is one, right? This is your question.
Don't do too much on it.
Just, yes. And then this is zero.
Are we ready to go over the triangles?
So zero. Sorry.
Oh, my God.
8 signs of.
I'm gonna call on two people in 10 seconds. Well, one person in 10 seconds. And then another person. Okay, the time for discussion is over. Right now, I just want to hear from the one and only Lee. Can you tell us what you did for number one? Well, the first triangle.
Yeah, so this time along, I noticed that, we over the time, we can go through side of movie.
So you started with sine of 70 equals b over 10?
Yeah,
Okay,
and then, once then back up.
so you got b equals. And this answer is called calculator ready. This is a great answer. It's exact. But I did ask for approximation. And did you have a calculator to do this? And what'd you get? What'd you get? About 9.4. Did everyone else get that? Thank you. And can you tell us what you got for A, just cutting to the chase? What'd you get for that? 3 what? 3.4? 3.2? Okay. Yeah, I wasn't sure if you were saying comma TOO or if I missed the 4 or, but is that right? Are we good? And of course, we could go back and double check and we notice, oh, that 9.4 is reassuring because P is bigger and it should be bigger because P took on a pretty big angle, right? Okay. Moving on. Leah, thank you for your help. Appreciate it. Max, did you get the answers for the second triangle? Can you just tell me what you got for C?
I got,
6.12, okay, and D?
I got 5.
Do we agree? Do we agree? Okay. Do we degree? Wait, is this is this degrees? How do you know?
I saw the, it doesn't have a degree sign.
Yeah, it's absent of a degree sign and it's in an angle.
Wait, so did it work?
Yeah, it's great.
I think 5.
Yeah.
Oh.
Can I answer any questions? If you did 0.7 degrees, that's a very small angle, and hopefully your C is very close to 8. And your D is very close to 0. If you did degrees, but that would be inappropriate.
No.
And we could change this to degrees if we just multiply it by what would have to go on the bottom. What has to go on the bottom for converting?
What do you do?
Well, this is radians, isn't it? Which means, oh yeah, pi is on the bottom one. You're saying it right. But don't do all that. Just put your calculator in radian mode or degree mode as appropriate. Okay. This one. There are no numbers here. What am I supposed to do? Yes, Haley.
all of the sides data.
Okay,
And then block all.
are we good with this, everybody?
Uh,
Oh, I'm just asking for the, oh, you're right, we don't know R. I guess we could say that R is equal to the square root of x squared plus y squared. We could do that. You're right, I said the missing sides, and in this case, R was missing, so thank you. Yeah, so there we go. Any questions? Oh, yes, Simon? Uh-huh.
I guess I did the, kind of 20 to be input the top and
Oh,
solve
okay.
the, A with that, but why can't we just do cosine of 70? It gives me a different number for A.
If you do 20 degrees?
Yeah, but like if you do, sine of, 20,
Mhm.
which is A over 10 and 10 times 20.
Sine of 20 equals A over 10, okay.
Yeah. And then you get a different number that way. If
You should get 3.4.
Yeah, but then first, second, if you do, cosine of 70, equals A over 10, gives you a different, like 10.
Cosine of 70 equals A over 10? It gives you the exact same thing, so there's probably a calculated error there. Because the sides are not changing. Is there a reason to go to that 20 degrees? Maybe more acute? I don't know. I wouldn't, but you should be able to. You're right. There should be security there. Have we seen this before somewhere? Right before the unit circle. We saw this already, didn't we? Okay, ready for the next exercise? Flip the page.
Oh my.
Oh, yes.
So we just find.
Well,
I don't know.
you know this letter right here?
Alpha.
That is alpha, and this other letter is beta. That one you know is.
Yeah.
I'm gonna cross out the theta. I don't want theta here. What I want you to do is mark the following angles in terms of only alpha and or beta. So this one, and this one. I want you to mark those angles in terms of alpha and or beta.
Yeah.
Wait, this way. Oh, only way.
Yeah, those two.
And then we know that 190 minus plus 90, so it's 189.
Yeah. Yeah.
I know the memories. The memories.
Oh, and those two can, oh, no. Oh, it's one.
189. Oh,
That 90 says.
Oh.
Wait.
Wait.
Oh, one minus 90 minus.
Oh, you're much.
Oh, wait.
Okay, the first one is. Are you good with 90 minus beta?
Oh, yeah.
Yeah. Complementary, and I should say that we're doing that in degrees, of course. Or 90 minus beta. I should say 90 minus beta degrees. That's good.
Oh, yeah.
They're complementary?
Yeah.
Well, all three angles add up to 180.
And that's 90 of our great, the one that there's. I don't know the other ways, but the one, this is the.
Okay, so that double arc, did anyone get what that one is? Yeah, did you get it? What'd you get?
Like 90 minus beta. Plus the double arc.
Okay, so maybe we'll call that y. So 90 minus beta.
That's the angle in between the 90.
Do we agree with that? That these two angles add up to 90? If you read that.
Yeah.
Because all three add up to 180, back up to 90. Okay, so what does that give you?
Well, I just looked at it. It should be, Y is equal.
Is equal to what?
Uh,
Is it beta?
Yeah.
Yeah. Can we see that visually here?
And the triangle beta plus 90 plus that one. Beta 90 plus same one. Beta.
You have two different instances of 180. But yeah, that angle is beta. And lastly, the triple. I'll give you guys about 20 more seconds to get that. Oh, the hint for this? I'll give you a quick hint. I'll start with this idea. See if that rings a bell.
Oh, the.
I'll just see if that rings a bell.
Oh, we're still okay. We're still okay. Oh my God. Okay.
You see it?
Oh, it's eight. Okay.
I'm gonna keep it this way. Okay, if you know it, I'd like to hear it on the count of three. If you know what I'd like to hear it on the count of three. 1, 2, 3. Are we okay with alpha plus beta? Because this angle and this angle are, those angles are congruent because they are all alternate interior angles are congruent. Yeah, that feels good, doesn't it? Bring that back a little bit. No. Haters. You guys haters. Okay, I'm gonna go back to black. I do need your focus. What we're gonna do is start labeling some lengths. We've done some angles. Let's label some lengths. Like you see that triangle that's in the middle of the rectangle with a hypotenuse of 1. Do you have any idea what the lengths of the legs would be if that's 1? Yeah, consider the back of the page that you just did, right? If the hypotenuse is 1, does it make sense that this is 1 times cosine of alpha? Right from the other side of the page, right? Isn't that what we just did? And then the opposite side would be 1 times sine theta. And I'm going to write that here just because there's room is scarce. Alpha. Did I say theta? Oh, yeah, alpha. Yeah, this is an alpha. That's how to handwrite an alpha. Alpha and beta. Beta is such a pretty letter. So nice. Okay. So we have cosine alpha, sine alpha. I like to measure or find the lengths of the two sides of this triangle on the bottom, the two unlabeled sides. Check with your neighbor.
I mean, cosine alpha. Beta times cosine
Okay. The bottom. Did he get it? The very bottom? Is it cosine beta? If this were 1, it would be cosine beta. But this length is cosine alpha.
Beta times.
So that's why it's. What, do you have it? Are we good with that? Cosine alpha times cosine beta? I don't know, I put the dot there. Tangent? We're bringing a tangent.
Tangent. Yeah.
Right, so for this, I just took the hypotenuse times cosine of this. I'm doing exactly this. I'm using this. To get the adjacent side, r times cosine. Oh, to get the opposite side of the r times sine. That's what I'm doing. It's just strange because the hypotenuse is cosine theta.
So adjacent side cosine alpha and cosine beta.
Opposite is,
Sine,
it's the alpha, it's the hypotenuse times sine beta.
cosine theta, cosine theta.
Cosine alpha, there's no theta.
Theta.
Yeah, this is hypotenuse times sine beta. It's hypotenuse times sine of beta. Can you find what other sides of that little triangle up there? The upper right triangle. Upper right.
Sine alpha cos.
You know what? You know what?
I'm gonna rush you through here. On the right side, it's sine of alpha times, it's adjacent, so it's cosine beta. The little one on top? Times sine, and it's sine beta because it's opposite of that beat. Now we've almost completed the sides of the rectangle, haven't we?
Yeah.
Do you know the other pieces?
Alpha.
Like this vertical one is gonna be, well, it's the hypotenuse, which is 1 times sine of, just a minute, sine of alpha plus beta. Nathan, you're doing great. This is a question fixed. You're correct though. And on the top, cosine of alpha plus beta. From here, we have 2 new identities. The first one is about sine of alpha plus beta. You see what it's equal to? It's a rectangle, so sine of alpha plus beta is equal to.
Oh my God.
We're gonna start with the top. Sine of alpha cosine beta plus. Do we see this clearly? Do you see clearly where that came from? That's one of 2. The other one is about cosine of alpha plus beta. I'd like you to make sure that you're able to get an appropriate expression for that one, considering what you see on the board. Check with your neighbor.
Oh, wait, no.
Okay, so we have that this is equal to what? Cosine alpha, cosine beta. Does it make sense? Minus that little piece up there, sine alpha, sine beta. Yeah, good. Well, let's see. We have cosine alpha plus beta on the top. If I want to get that length on the bottom, I start the whole thing.
I was not.
Yeah, and then we have to subtract the little piece. There are 2 more identities along with this. Bear with me. There's also, oh yeah,
Oh, I understand.
you see it? I hope that, do you see these on everything we just did?
Yeah.
Nathan, you with us?
Yeah.
Okay, 2 more. If we have alpha minus beta, then the equation is going to change on the other side to the same thing with a minus. If we have a minus for cosine, on the other side, it's going to change to plus. And notice I'm putting a plus underneath just so that we're lining up. right? Like this plus goes with this plus. But this minus goes with this plus down here. So we have, it's kind of like just opposites. Yeah. Okay, so we're gonna do a few problems with this in mind. So have this ready while I give you a couple problems. And this is the end of your notes, not from the packet still. Where do I have this? This is under warm-ups for you guys. Up until now, we haven't been able to do cosine of 75 degrees. But today we can. We can figure out exactly what cosine of 75 degrees is. If I break this up into something that we know,
Oh my gosh, yeah.
50 and 25,
45, 30.
does that make sense to break this up into 45 plus 30?
That's
And I'm going to use the equation that we just came up with. Cosine of alpha plus beta is equal to cosine alpha, cosine beta. Its cosine is going to be opposite. Sine alpha, sine beta. So using this, you see what we're going to do? Cosine of 45 degrees times cosine of 30 degrees minus. I'll let you finish. Do you know cosine of 45?
yeah.
Root 2 over 2. Do you know cosine of 30? What is it? Is it root 3 over 2? Yeah, now we have to reference the unit circle. Sine of 45. Root 2 over 2. And sine of 30, we know that one. It is pretty cool. So what we have is the square root of, could I combine those? Square root of 2 times square root of 3?
Yeah.
Multiplications as we can. Square root of 6 over 4. Yeah, multiplication of fractions. Think back to 5th grade. And oh, look, common denominators. Root 6 minus root 2 over 4. Woo. Oh, that's the problem I gave you. I said, hey, let's try this. And then I said we could break it up. And then I need to erase that to the references. I hope that this makes sense. That was a ton of stuff. But that gives you a lot to do over the weekend, right? Yeah. 3-day weekend. Yeah, we have the homework gonna be on Pearson. Thank you for asking. Pearson tonight. What's that? Quiz is Wednesday. I'll give it back to you next time. There's still some people who didn't take it. There's still a couple of people who didn't take it. Test is on the 19th. The day before you get up.
I'm saying like this.
Oh, yeah.